Okay, good afternoon, everyone. I will speak in English, although my speech was supposed to be in Czech, but we'll see if anything happens. Okay, perfect. I hope that it's okay when I speak in English. I'd like to show you that also in Czech Republic we can do quite interesting research in exoplanetary topic, and that also you as observers can contribute significantly to this field. So first, some motivation. Why to study exoplanets? Of course, the basic question that contains, I think, everything, and that mankind asks since its beginning is: are we alone or not? What is our place in the universe? How did we get here? So this is the basic question, but we also want to know how the exoplanets look like, how the systems look like, how many of them are there, if they are similar like our solar system or not. It's also, this field is, I think, very attractive to the public, so everyone is interested in exoplanets now. But this topic, this field of research is also important because it puts extreme demands on instrumentation, on methods, on techniques. So it pushes the limits of our knowledge. The ideas about exoplanets are quite old because already in the 3rd century before Christ, Epicurus was thinking about some other worlds that can be similar or completely different than our Earth. And it took quite a long time till the first exoplanet was detected, and it was in 1995 when Michel Mayor and Didier Queloz discovered the first hot Jupiter orbiting solar-like star. Of course, now we know lots of exoplanets, and if there are among you somebody who doubts that there are exoplanets, here you can see, actually it's an animation, but I had to convert it into PDF so you can see it in a static form. So here you can see a distant star which is orbited by 4 exoplanets, so they are really there. And currently we know about, let's say, 4,000 exoplanets and many other candidates. And if you check this distribution, you can see that most of them were discovered in 2014 and 2016. And this was by space mission Kepler. When the data were released in 2014 and 2016. And these green bars show how many exoplanets were detected by transit method. So most of the exoplanets, or known exoplanets, were discovered by transit method. Here at this plot, you can see the distribution of planetary masses versus its orbital distance. You can see that currently our solar system seems to be quite strange, quite different from the other systems, but we don't know actually how the real distribution looks like, because we are strongly biased towards big planets that are orbiting very close to their host stars, so we actually don't know the real statistics now. At this plot, you can see what we actually want to know, because if you know the size of the planet and if you know the mass of the planet, you can calculate the density, and you can estimate if you are observing a rocky planet or a gas giant, and that's crucial to know. Just to put your attention, check these error bars in mass. This means that a lot of work is before us. So that's the parameter that we don't know precisely in most of the planets. I will focus on 2 methods because these are very simple. The ideas of these methods are very simple. The transiting method, you just observe star and look if it dims or not. just by investigating the brightness of the stars. This method is very nice because you can estimate relative size of the planet. And if you know the size of the star, you know the real value of the size of the diameter of the planet. From the depth of the transit, you can estimate the diameter, but you can also, from the shape of the transit, estimate the inclination, which is also very important because by the method of radial velocity measurements, you can get the lowest limit for the planetary mass, and there is a sin I. So when you estimate the inclination, you can put it there, and you can get the real mass of the planet. Here, just to give you some ideas how precisely you have to measure. If you were a distant observer and want to detect Jupiter, then the dimming of our sun would be something like 1%. In the case of the Earth, it would be 100 of a percent. So very, very shallow decrease of brightness. And in case of radial velocity measurements, if you would like to detect Earth around our sun, then the Earth moves our sun like 0.1 meter per second, which is, let's say, below our capabilities right now. But there are state-of-the-art instruments that are built now, which should measure exoplanets with this precision. Stefan? So, because we are in Czech Republic, I have to mention the first transit that was observed from Czech Republic. It was made by Ondřejov here in Brno with 40 centimeter telescope at the observatory and planetarium at the hill. I also have to mention the campaign which was in 2008 when the exoplanet HD 189733 was observed by several observers with different instruments. You can see that also with the instrument with aperture of diameter of 34 millimeters, you can detect transit. So it's quite easy now to detect transits. Of course, I have to mention that the section of variable stars and exoplanets of Czech Astronomical Society maintains and provides some important tools, some useful tools. So it's the exoplanet transit database and project České. You can upload your data. The time of the minimum of the mid-transit will be automatically calculated. And it's very useful, and it's used by observers not only from Czech Republic, but also from abroad. And it's really famous. People know it around the world. Okay, so what else? We can detect transits, we can monitor them, but what else can we do? Can we discover new exoplanets? Can we confirm exoplanetary candidates coming from some missions, from some surveys? Can we even study exoatmospheres? Let's check this. Currently in Czech Republic, there are two groups that are interested in exoplanets. The main group is in Ondřejov at the Astronomical Institute, and this group was founded in 2015 when Petr Kabát came back to Czech Republic from his stays abroad, and he established a new working group. I'm still a part of this group because I joined them last year, and since I'm now at the Masaryk University, I established a group of students also here. You can maybe recognize some of them because some of them are also here. So we can definitely discover exoplanets. Actually, it hasn't happened yet, but I think that Pavel Cekář was very close to discover the first exoplanet from Czech Republic. So you need to monitor some portion of sky, some part of the sky for a long time. This is what Pavel does. He observes some selected fields. And check if some of the star changes its brightness. And Pavel is very efficient in mining the new variable stars. And he was able to detect something like this, transit-like event. With this depth, about, I don't know, 2%, 1 and something percent. So this is very nice candidate. But if you observe it for a long time, you can realize that you actually observe only secondary minima of some algal type binary. So it's crucial to know if the candidate is really exoplanetary candidate or if it's something else. The other thing is that you need periodic blending because your target can mix up with some close other variable star, let's say binary, and you just observe mixed light. So, for example, this is the aperture of the test satellite, which is now observing, and you can see that the resolution is quite poor. It's similar to other surveys. For example, Superhost has the resolution of 13 arcseconds per pixel, so it's very bad. And this figure shows the same. So you can see this star, it's this star, this is this, so it's mixed. And you need to know if you observe really only one target or something else. So this is what we can also do from Czech Republic, and you observers can do it. Now I stop for a while at radial velocity measurements because we started to use the echelon spectrograph, which is mounted on 2-meter telescope in Ondřejov. Petr Kabat and his group started in 2015. Actually, we observed since 2017, so just 2 seasons. Because this instrument was built in 2007, but it never had been used for some reasons. So actually, nobody knew how to deal with that. It's homemade instrument, I have to say, but it works, and this is very important. So it has quite a good resolution, 44,000, and the magnitude limit is about 12 magnitude. We observed the star which has 12 magnitudes, and with 1.5 hour exposure we could get signal to noise 7, which is not much, but okay, it could be used in some way. If you check the formula for the uncertainty of radial velocity measurements, so it's dependent on the resolution, which is quite good in case of Ondřejov spectrograph OS, and it's also dependent on the range of wavelengths you use for the cross correlation of the spectral lines, and that's why it's very advantageous to use echelon spectroscopy and echelon spectrograph, because single order spectrograph offers you only very narrow range of wavelengths. But as you can see here, in ideal case, you can use very broad range, very broad spectral range. I just wanted to demonstrate that even with this instrument, which suffers from some shortcomings, you can see that the red part of the echelon suffers from fringing, which is caused by the coating of the CCD, the thin layer which coats the chip. Then the orders in the red part overlaps, so it's sometimes difficult because the light appears, the lines appear in more than one order, which could also be a problem in very bright targets. The spectral lines are tilted. This is another disadvantage of this spectrograph. It's because of the design of the instrument. The other thing, you can see that the spectral lines here are somewhat blurred. Nobody knows what caused this. Yeah, it's nitrogen cooled, but it's refilled manually. So this means that every night somebody must go there and refill the nitrogen, which is also not good for the stability of the instrument. And we take the thorium-argon calibration spectra before or after the exposure. We are not able to calibrate them, to observe them simultaneously. Okay, so there are some disadvantages, some shortcomings, but we can overcome them. And we tested stability of this spectrograph, and we get quite good results. I would say very nice good results, because the stability over one night is about 18 meters per second, just by using thermal lines for the calibration. If we check how the stability looks like during 1 year, so it's about 300 meters per second, which is fully comparable with other instruments. You can see here measurements from Tautenburg, which is also 2-meter telescope. It's a twin of the Ondřejov telescope, and you can see that during, I don't know, 1 month, the stability is similar, like in Ondřejov. So we got very good results. By using iodine cell, we can get precision or scatter something like 20 meters per second, which is amazing, just amazing. To detect hot Jupiters, you need to measure precisely, let's say, I don't know, a few hundreds meters per second. To detect Earth, you need to measure 2 meters per second or better. So, okay, this instrument is not for investigation of exo-Earth, but we can at least confirm exo-Jupiters, hot Jupiters. And this is actually what we started to do. We selected a few bright targets and observed them, and all of them appeared to be binaries. As you can see here, because the amplitude is in order of kilometers per second, and also the light curve does not look like exoplanetary light curve. So these are just few examples of our work. We also detected very interesting target, which has this light curve. These are data from Kepler-2 mission, and it could be explained as some spotted star, as probably some city star with some transit. And it's very interesting because there are very few such objects known today. There are also alternative explanations that these variations can be caused by some disk. This star shows delta Scuti-like pulsations, so it's a very interesting target, and we will propose some proposals to bigger telescope to get more data. Okay, this was also a movie, but since it's a PDF, it's not a movie, it's just a static. We hope that we will be able to observe also exoatmospheres. And the idea is very simple, because if the Earth, the exoplanet crosses its host star, then the different compounds absorb at different wavelengths. So if you measure transit depth and other other characteristics of transit at different wavelengths, you can get some idea what could be the composition of the atmosphere. So here you can see just an example of such measurements. Of course, this is done with the biggest telescope, with DLT and such instruments. But it's possible. And the other idea is that you just measure spectrum out of transit and in transit. And you just subtract them, and if there is some residual at a particular wavelength, that's a good sign that the element is there in the atmosphere. This is the plot which shows the probability that you will detect signal at the planet with 2-meter telescope. So we just take some data from 2-meter telescope from Ferros and injected there the variation from HD 189733. And if these planets have the same abundance of sodium as this planet has, then we should be able to detect For example, in Kelt 9 and Mascara 2, the exoatmosphere, with 2-meter telescope in Ondřejov. We should be able to do that. We have lots of spectra from this year, and we will try to detect the atmosphere. But yeah, let's see. This is just an assumption. So we will see how we perform. Okay, we can also do spectral typing because this is crucial for the determination of the characteristics of exoplanet. Because the better you know the size and other characteristics of the host star, the better you know characteristics of the exoplanet itself. And this plot shows 200,000 targets from Kepler input catalog as seen by Gaia. And this is the difference between Kepler input catalog and Gaia. And you can see that the difference is quite huge for most of the stars. So if there were planets that were supposed to be exo-Earth, they could be easily hot Jupiters, actually. Just because you do not know precisely the parameters of the whole star. So this is what we can also do in Ondřejov spectral typing. I'm sure that you noticed that in April, the test was launched, April 18th. This is a figure from this satellite, and this satellite is starting to produce data. It is supposed to scan the whole sky within two years. It started to observe the southern ecliptical hemisphere, and next year it will turn and will observe the northern hemisphere. But actually, the targets from sectors 3, you can see that the most northern camera has a center at declination -12. And since the field of view is 24 degrees, so some of the targets are already observable from here, from the northern hemisphere. And from sectors 4, 5, 6, 7, and so on, I think maybe 8, these targets will be observable from Czech Republic. And this is a big chance for us because TESS will observe preferably very bright targets which we can follow up with the 2-meter telescope and also with small telescope photometrically. So this is what is going to happen, and we are really looking forward to this data to select some candidates and to start measuring them. Okay, so I think that also here in Czech Republic we can contribute significantly to solve the question if we are alone just by studying exoplanets. So thank you for your attention.